Okay, in this final section, we will discuss logical proofs. We will build off on what we did in the last couple sections with learning the rules of inference and rules of implication and replacement, and we'll begin to construct logical proofs. In many ways, what we've done in this course will prepare you for more advanced symbolic logic. And in advanced symbolic logic, you would conduct proofs that go on for 40, 50 steps and can become very complicated and require a number of different steps and so on. So this sort of gets you prepared for that. So what we'll do first then is we'll talk about the rules that get used in doing a logical proof. Much of this we have already discussed in previous sections. The rules of implication. In logical proofs, there are 8 rules of implication and 10 rules of replacement that are used to move from step to step in an argument on the way to deriving the conclusion one has set out to prove. So if we think about a proof is trying to get to the top of a mountain, let's say, then these rules of implication and rules of replacement are the tools that you would use in order to get to that point. And it's not always clear which tool you'll need, and so sometimes you'll have to use some guesswork, or you'll try one way to do it and it doesn't work, and then so you go back and do another way. Sometimes you go a roundabout way and you end up getting there. Ideally, the most beautiful proofs are the ones that get there in the shortest, simplest way, get to the conclusion. Most of the proofs that you will be dealing with in this section are all of the simple variety, and you won't need any long multi-step digressions in order to get one premise that you need in order to go on and get the conclusion proven. But you will get some of the basic ideas of how you go about doing a proof in this section. So in this final section, we will only cover the 8 rules of implication. But this will prepare you for more advanced symbolic logic and the proofs this logic entails. So let's go on and discuss the rules. So the first 4 rules are modus ponens. We have discussed this. So imagine we have a proof of a number of premises or steps. As long as each step has been derived at by a valid logical inference, then each step preserves the truth value of the preceding steps. So a modus ponens would be as long as we have a P implies Q and a P anywhere in our previous steps. It could be step 2 or step 22. They could be separated by as many steps as we want. As long as those 2 steps are there, we can conclude Q. And remember, the modus ponens is the form of the argument. You could have anything, as long as it's a complete statement, stand in for P, and anything, as long as it's a complete statement, stand in for Q. And as long as the statement stays the same, that statement that was standing in for P is the same later on in another step in the argument, you can then use modus ponens. We will see that in some of the examples as we go forward. And that's going to be true of all these rules. These rules basically lay out the forms of arguments, and how you apply these rules is going to vary from different argument to argument, but the form will always stay the same. And these forms are all valid. Okay, so modus tollens is similar to the modus ponens, except it's not Q implies not P. Pure hypothetical syllogism, we have P implies Q, Q implies R, and we conclude from that that P implies R. And the last one of these first 4 is the disjunctive syllogism. If we have P or Q, then we have not P, we can conclude Q. This is something we discussed a couple sections ago when we talked about valid argument forms. We are now simply memorizing these argument forms as the rules of inference or implication that we use in constructing a logical proof. And the next 4 of the rules that we need to know are, number 5 is constructive dilemma, which we've also talked about. If you remember the example of dogs and cats and fur balls and fleas, then that's where the constructive dilemma comes in. Simplification, if we have P and Q, we can simply separate out P. Okay, that's the only time we can do that. We can't do that if we have P or Q. We can't separate out P. It has to be P and Q. Then we can separate out P. conjunction, we have P and Q on separate lines. We can always add them. And this is true of any statements. Any two statements we can add together. So sometimes if you're using constructive dilemma, for instance, if you have a hypothetical, and you have two hypotheticals, you can add them together and potentially use the constructive dilemma. We will see that, especially in the exercises. We will see some examples that do just that. So again, remember, it's the form of conjunction that's important. You could add very complicated statements to one another. And finally, the last one is addition. Addition, if you have P, then you can add Q. And this is important because if you have a proof and you have a letter or variable that's not in or among the premises, you can simply add it. Okay. Now, this doesn't mean you could add anything you want, because you can't add, if you had Q, you can't simply add not Q, because then you would be adding a contradiction, and then you could go on and prove anything you wanted, and so that is not allowed. But otherwise, you can add Q or any other thing that you might need in a proof. We will see some examples like that as you go through the exercises. So let's go on and do an example of a logical proof. Okay, this is the first of 3 proofs we'll do to show how you apply the rules of implication. This is a fairly simple one. You can see here we have the first premise, and one thing to remember is you have to make sure every line is numbered, because these lines will be important as you go later on, especially in longer proofs. It helps keep things organized and helps people who follow the proof to see where you got your various premises from. So here the first line is A implies not B. The second line is C implies B. Third line is A, and we are asked to prove not C. That's what this / does. It sets apart what we're asked to prove. So the first strategy to follow is there a C among the premises? And there is. And so the next question asks, how can we get a not C? And this is where becoming familiar with all the rules of implication will help, because we know, if we look at the rule modus tollens, for instance, the MT rule, that if we had not B, then we could end up with not C. That would be how modus tollens would work. Do we have not B? We have not B here, but it's part of an implication. We can't just simply take the not B out of that statement. If it were a conjunction, A dot not B, then we could, but we would have to get the not B by itself by another way, and that other way would be modus ponens. So if we had A, then we could conclude not B, and we do have A on the third line. So now we can go about making our proof. So on the fourth line here, we can plug in A, and then A implies not B to get not B. This is modus ponens with 1 and 3. So lines 1 and 3, modus ponens. And now that we have not B, we can then get the not C through modus tollens by lines 2 and 4. And there we go. We have proven it. That's our first. Let's move on to the second. Okay, now we're moving on to proof number 2. And line 1, it's F implies G. Line 2 is F or H. Line 3 is not G. And line 4 is H implies G implies I. And we're asked to prove F implies I. Anytime you're asked to prove an implication, one way to think about that is whether we can use the hypothetical syllogism rule. So we do have F implies G. So if we can end up with G implies I, then through a hypothetical syllogism rule, we would end up with F implies I. So we do have G implies I right here. The only way we could get that, though, is if we can end up with H. We have H here, but how can we get H? We need to get H off of this statement by ending up with not F. Because if we had not F, then we could use disjunctive syllogism to end up with H. How can we get not F? We have not G, and we have F implies G. So through modus tollens. See, as you become more familiar with all the rules, you will be able to see how you can get to where you need to go. Basically, you start working backwards. You start where you want to end up and see where in the premises you have what you need in order to get where you want to end up. So let's begin our proof. So we decided, right, that we wanted to end up with not F, so we can use disjunctive syllogism. So let's end up, we can get the not F by 1 and 3 modus tollens. And now that we have not F, we can get H by itself by disjunctive syllogism of 2 and 5. Now that we have H, we can get G implies I by itself by modus ponens. That would be 4 and 6 modus ponens. And now that we have G implies I, we can get F implies I, because F implies G, G implies I, by hypothetical syllogism. We can infer F implies I by 1 and 7 hypothetical syllogism. That's it for proof number 2. Okay, this is the last and third proof that I'll show you, and as you go through the exercises for this section, you may use other rules like constructive dilemma. Very often when you have a proof that requires disjunction like S or T, you'll often need to use the constructive dilemma rule. It turns out that that's not the case with this one, but you'll see in some of the exercises that that will be. And I will have another example that I'll give with the exercise keynote where I go over one of the examples with constructive dilemma. But basically the idea is, as we've seen, each step of the way you plug in one of the rules of implication, one of those 8 rules, and if it fits that rule, then you know the conclusion follows. It's valid. Again, all the truth tables and everything we've been doing in this course so far has led us up to this point of being able to do a logical proof. So let's go through this example. So we are asked to prove S or T. And how can we get S or T? Well, the reason we can't do constructive dilemmas because we don't have all the things we need here for constructive dilemma, but we can end up with, one of the things we don't have, for instance, is we don't have T anywhere in the premises. But as we know from addition, we can add anything we want, as long as it doesn't contradict something that's already there. We couldn't, if there was N in here, we simply can't add not N. That would lead to contradictions and we could prove a falsity from true premises. So, but we don't have T here, so we know we can add a T. So what we want then is we want to end up with S by itself, and then we just add T. So that would be our last step. So how can we get S by itself? Well, if we can get not P and Q, then we, through modus ponens, could end up with S by itself. So how can we end up with not P and Q? Well, we can end up with Q by simplification. So let's do that. And as you'll see, you can, if you compare this with examples in the book, you can go about it in different ways. As long as each step is valid and you end up with the conclusion you wanted to end up with, then that's fine. So here we go then with Q by simplification from line 3. And now we want to add not P to Q, but we don't have not P yet. But we do have P implies M, and if we could end up with a not M, then through modus tollens we could end up with not P. And we do have a not M here, a not m conjoined with n. And so through simplification, we can end up with not m by line 1 simplification. And now we can end up with not p through not p through modus tollens 2 and 6 modus tollens. And now we can add not p and q by a conjunction of 7 and 5. And now we have not p and q implies s, and so through modus ponens we can end up with s by itself by lines 4 and 8 modus ponens. And now we can simply add t to s by line 9 addition. And there we go. That's our final proof. Hopefully this will help you with your exercises as you go on and do your own proofs. Another thing to keep in mind before you go through the proofs are certain strategies. The first couple of sections of Chapter 7 offer a number of strategies to follow in figuring out how best to go about proving the conclusion. So be sure to familiarize yourself with these strategies, especially the first one of working backward from the conclusion to finding what you need for the conclusion in the premises. But there's a number of other strategies. I've given some in this section already. If you have a disjunction that you want to prove, then sometimes you might want to look to constructive dilemma as a possible way to go, or addition, and so on. So there's those strategies will be very helpful for you to try to chart a strategy to go about proving that conclusion. So here's the exercises for this section, and give it your best shot. I think it should be, if you follow, the one thing about these, if you follow each step and you have a valid move each time, you'll know you're doing it right. And what we'll do in the exercises videos, we'll go over a few of these examples in order to kind of show how some of these proofs can be constructed. But that's it for this final section.